probably just before we start, I'm going to quickly cover what we did last week, basically just to summarize. So we mainly discussed the Cauchy stress tensor. We said there is different types of stress tensor. The one we are interested in this course is going to be the Cauchy stress tensor. And there is specific properties for this tensor, but the most important principle behind the Cauchy stress tensor is that the stress at any point, so if you have an object and you cross this object using a plane, you cut it using a plane, then the stress, probably this is the cut surface, then the stress on this plane is only dependent. So this is the stress vector. I'm going to call it probably Tn. So the stress vector on this plane is only dependent on the normal direction to the plane itself. So it's only dependent on this end here. Okay, so this is pretty much the main principle behind the Cauchy stress tensor, and is actually defined, and everything to do with this stress tensor is based on this assumption. Now, this will be reflected on the math in terms of two equations, basically. And as I said, I mean, this is something probably also for you to remember is when you want to find a projection on a plane, you need to multiply with the normal to this plane. So this is one thing. And then the other thing, you always define planes. I mean, there's different ways to define plane, but the way we use in continuum mechanics is to use the normal directions. Usually the normal direction to a plane will define this plane. Okay, so it will define a unique plane. There's other ways as well, but for continuum mechanics, we are going to strictly define planes using normal directions. So this will reflect in terms of the math as Tn, this is the stress vector, is equal to the stress tensor, T, multiplied by the normal direction. Okay, so this is the first thing. Then if we are interested in finding the normal and the shear components of this one, this is a vector. So if you want really to find the normal and the shear for that, to find the normal, we multiply it again with the normal direction. So I'm going to call it Tn, and this is a scalar. So the normal component is just Tn multiplied by n again. So you just take this vector and multiply it with n, and you get the normal components. As I said, if you are looking for projection, multiply with the normal. Then the other thing is you want to find the shear component. So the shear components will be can be obtained using the Pythagoras rule. This is basically Ts squared is equal to the length of T. So this vector, you are taking the norm of that. So this is the length, square root of the sum of the squares for any vector, minus Tn squared. So if you find, if you are interested in the shear component, they just find the length of the shear components, because as I said, this is the vector T, and the length in this direction will be the normal, and the length in this direction is going to be the shear. So this is Ts and this is Tn. So if you take the square root of the sum of the squares, you get the length of the vector. So we spent some time also explaining why this stress tensor is a second order stress tensor, and explain why this is going to be the case. I mean, we did a derivation for that, and we said eventually this is a stress tensor. This T here is a stress tensor, and it's called a second order stress tensor. So it is a second order stress tensor. Everything to do with second order stress tensor would be applicable to this second order stress tensor. Now, the most important thing is the principal stresses and the principal directions. Right? So you remember when we discussed a tensor, we said one unique feature about every stress tensor, or every tensor basically, is to identify unique principal directions and unique principal values. So for the stress tensor, T, we are going to have three principal stresses. So this is T1, T2, and T3. And you are going to have normal directions associated with this. I'm going to come back to this concept, trying to explain a little bit what does it mean in physical terms. But for the time being, this is just a mathematical problem. We're just solving an eigenvalue problem, eigenvalues and eigenvectors, just like we did probably for earthquake engineering. I think you probably have seen this eigenvalue problem quite repeatedly. So this is a very famous property of matrices, basically. Okay, so there's many advantages for solving for eigenvalues, but in terms of stress, this will reflect in terms of the principal stresses and principal directions. I'm going to try and explain this a little bit later today as well. Okay, so these stresses would happen on certain planes. So these planes are identified using the principal directions. I'm going to call them N1, N2, and N3 for the T1, T2, and T3. Now these values here express the maximum normal stress that you can achieve anywhere. I'm going to explain it in a bit more details, but for the time being, let us assume that you have this stress tensor. I'm going to call it sigma 1, 1, sigma 1, 2, sigma 1, 3, 2, 1, 2, 2, and 2, 3, 3, 1, 3, 2, and 3, 3. So you have this general stress tensor written in terms of this coordinate system, x1, x2, and x3. You rotate the coordinate system x1 dash, x2 dash, and x3 dash. We're going to get a second stress tensor. I'm going just to call it sigma dash. Now, sigma dash is not the same like sigma, so these are two different matrices, but they both express the same amount of stress. Now, in terms of the stress that's happening at this point, you have a specific stress tensor. If you change the coordinate system, the matrix will change, right? Now, what is not going to change is the nature of the stress. Physically, you are still expressing the exact same physical phenomena. It's not changing. Now, there exists a specific coordinate system. I mean, you keep rotating this coordinate system. You keep rotating this and try to change the coordinate system and keep changing it. You will get to some point where this is going to be projected into exactly this one. Sigma 1, 0, 0, 0, and sigma, I'll probably just call it 1, 1 for the time being, 2, 2, 0, 0, 0, and sigma 3, 3. So what you have done here, you found a coordinate system. I'm going to call this one sigma dash dash. So there exists a coordinate system where this stress is entirely projected in the normal direction. I mean, this is going to act only in the normal direction. So what you are doing here is just projecting everything. All these components are projected into the normal direction. Now, it's going to be very difficult to imagine things as they work in tensors, but I'm going to try and explain it a little bit in terms of two-dimensional examples. I'm going to solve an example probably later on, but for the time being, I'm just going to try and explain it in a two-dimensional plane. Now, what I'm saying is mathematically wrong. What I'm trying to explain now is mathematically not correct, but it will give you an understanding of how the stress would react. Now, think about that. You have a coordinate system. I'm going to call it x1 and x2. And then in this coordinate system, you have a quantum particle, and this quantum particle will undergo some stresses. I'm going to call them sigma 1, 1, sigma 1, or sigma 2, 2, and then you have some shear stresses, so sigma 2, 1, and sigma 1, 2. Right? I said, if you remember from last week, the second index would express the plane. So this plane here, this is the normal direction. And then the first index would express the direction of the stress, which is happening in this direction. Okay, so this is where I got this. Now I want you to imagine that you are rotating this square here. And think about these quantities here as vectors. So try to rotate this into some angle. And then these two components, this one and this one, will also be projected into a normal direction and then a shear direction. You can imagine that this shear direction will probably be more close to this direction here rather than the normal direction. If we try to sum them up in the normal direction, you see that the summation is probably smaller, but it's still expressing the exact same amount, but that is only changing in the direction. I probably just try to draw the Mohr circle for this example. I think the Mohr circle would also help you to understand. So this is again x1 and x2. I probably just write the stress tensor for this case. This is going to be sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. And then when you want to draw the Mohr circle, this is sigma. In the normal direction, this is the shear component. So the shear component would be sigma 1, 2 positive and sigma 1, 2 or 2, 1 negative, as you wish. And then you have some number for sigma 1, 1 and some number for sigma 2, 2. Let us assume that this is how it looks like. Then in this case, the Mohr circle would look like this. I mean, you can cut it at any corner you want, but eventually this is going to be one point and this is going to be another point, and then you draw this length and you need to draw a circle. Oops. Yeah, it's going to be tricky to fit the circle here, but so on the circumference of this circle, any point would represent the exact state of the stress. And if you get to this point here and this point here, you will get the maximum possible normal stress, where you have, I mean, assume that you have the normal stress here or the normal stress here. You have the maximum possible normal stress. This is going to be the maximum possible sigma 1, 1. And at this exact point, you have zero shear point, right? And then you have the minimum possible normal stress is going to be at this point, and then at this point, you have zero shear stress as well. So it's very much like this circle piece. Okay, now this is not happening in 2 dimensions. What is happening is a tensor that is actually active in 3 dimensions, active in multiple directions. And then you need to imagine something that is actually being projected all the time in 3 dimensions. I don't think it's possible to imagine it. It's just something that's happened in this. I mean, this is a phenomenon that would happen in this way. And the easiest way probably to imagine it is to try and see the vectors. All right, do you have any questions about this? I suppose this is fine. Okay, so how about the shear stress then? How about the maximum shear stress? So the maximum shear stress, if you look again into the Mohr circle, will be at this point here, and then at this point. So this is going to be the maximum possible shear stress. This is going to be tau max, and this is going to be tau minimum. Now, at the maximum shear, you cannot get, I mean, in the general case, you don't get zero normal stress. What you get is going to be some value for the normal stress. So think about it in this way. In general terms, it's not possible to project the stress only into shear. It's going to always result into some normal component. It's possible to project it into the normal direction completely, but not completely into the shear direction in general terms. All right? So if you look into the set of, if you want to look into the 3-dimensional case, then you have maximum principal stress 1, 2, and 3. So how about the maximum shear stress then in this case? How do you get the maximum shear stress? Well, there is some derivation to get the maximum shear stress. I mean, it's not in 2-dimension. In 2-dimension, Moore circle will get it for you. In the 3-dimensional case, you need to follow a certain procedure. I'm going to show you the derivation for the procedure. I don't expect you to go through the entire procedure, but I just want to show it to you one time, and then I'm going to show you how to find out the stress in 3 dimensions. So this is the principal stresses. You get them by solving an eigenvalue problem. And I'm going to state a convention. This convention will become quite handy later on. When you get the principal stresses, put them in order. So you have the maximum principal stress, the absolute maximum to come first. The minimum one, the absolute minimum, or not the minimum, the minimum real number. So if it is negative, then it's going to be smaller than a positive number. And then the one in between is going to be the second one. So you order them so that you have the largest, then the smaller, and then the smaller. You put them in this order. This is just a convention. It's not a requirement. It's just a convention that will simplify our life later on. All right. Now I want to find where the maximum shear stress is going to happen. I'm going to use this rule here. This rule here. I'm interested in finding the maximum shear. This is the maximum shear. So I'm just going to create a general normal direction. I don't know what is the plane where the maximum shear is going to happen. I'm just going to assume that this is going to be a general normal direction. I'm just going to call it N1, N2, and N3 for N S max. All right, so I have the NS max, some normal direction to a plane that I don't know. We'll have some general expressions, N1, N2, and N3, and this is a normal direction, so the square root of the sum of the squares should always be 1, is equal to 1. Okay? Now, I have this general normal direction. I'll just multiply it by this stress tensor. I just multiply these two together, N1, N2, and N3, multiplied by the stress tensor, the general one, and then what I get is going to be this Tn here. All right, so I have the normal, I have the stress vector on this very general plane. I don't know what is the plane, but I know that the normal, the stress vector is going to look like this. So this is the first thing. And then I can next calculate Tn. From that, I have the normal direction. I'll multiply it one more time with this one. In this case, I have the normal component for this vector here. And then to find the shear is going to be this one. Okay, see, I've got the shear in terms of the general vector n. Now, if you do that, if you follow this procedure, you'll get this expression here. This is just the length of the vector, Tn, is the square root of the sum of the squares. Since I'm doing Pythagoras, I just use the square here, and then I don't have to take the square root of anything. All right, and then I'm subtracting T, sorry, this is Tn, T capital N. Okay, so this is a vector. I'm calculating the length of this vector, and this is the square, and then this one here is just the multiplication, or this is just the projection in the normal direction. Subtract both of them, and I know this rule here, and then I end up solving an optimization problem. Okay, so it's not quite easy to solve. It's a nonlinear one. So I need to find the principal, or I need to find the maximum and the minimum of this equation. I have 3 variables. All the 3 variables are squared. So this is N1, N2, N3, and they are not linear. They are quadratic. So I have 3 unknowns. They are quadratic, and I have a second equation for them as well. I need to solve these 2 equations, and obtain an optimum solution for that. Now, there is a certain mathematical procedure. I'm not going to get into the details of the mathematical procedure, but what you do is you find the derivative, just like you do for the quadratic equation for a single variable. You find the derivative, and you use Lagrange multipliers in this case. I don't assume that you know Lagrange multiplier, but it's a standard mathematical procedure for optimization. Now, if you follow this procedure, so you find the derivatives, and you multiply by Lagrange multipliers, and you solve this optimization problem, then you get the plane, you get values for n1, n2, and n3. Now, this is going to be a set of rules for the general n1, n2, and n3. So it's going to be a bit lengthy. Now, the convention I've explained earlier will come handy in this case. If you put and basically it's going to be different cases for different possibilities. You need to basically cover all of them. But if you follow the procedure I've explained and take the maximum to be 1 and the minimum to be 3, then the maximum shear is always going to be T1 minus T3 divided by 2. And then the normal on this plane, I'll just go back to the Mohr circle here. You remember I said the normal amplitude of the stress at this point is not going to be 0. In the general case, it's going to be some number. So this number is going to be T1 added to T3 divided by 2. All right? And then where's the plane where this maximum shear would happen? The plane where the maximum shear is going to happen is going to be, I'm just going to call it NS max. And this is a vector, is going to be plus minus 1 over the square root of 2 multiplied by n1 added or subtracted from n3. Okay, so it's not going to happen on one plane, it's going to happen on 4 planes. It's going to be plus minus and plus minus. I'm going to solve an example and then you see all the possibilities in this example. Okay, so if you follow this description here and this description here, you don't need to worry about this. Just forget about the tree.